Okay, this is a quick video discussing the concept of the full definition of a limit, as well as how it leads to what I call mathematical voodoo. Now, I'm posting this video both in Calc 1 and Calc 2 because it'll show some things about the limits that sometimes get overlooked. Early in Calc 1, we bring the idea of the limit in, and if you are seeing calculus in the right way, the limit is the leading force of calculus and not the derivative or the integral. And the reason why is what I call the voodoo. So an example of that is the thing over here. Let me first start off with the definition, which is not something we emphasize a lot in our Calc 1 course, and you definitely don't see it in Calc 2 because it's old material. But we write that limit as x approaches a, if f of x equals L, if for all epsilon greater than 0, there's a delta which can be a function of the epsilon greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. So the idea is, if I think at A, f should be the value L, but no matter how narrow I make this vertical window here, I can find a vertical window that keeps the graph within the vertical window. I'm not going to go into a lot of details there, but one important thing I want to highlight is this part right here. In the definition, this one's often part overlooked, and what this says is that x does not equal a. Because if x equaled a, then the absolute value of x minus a would actually be 0. So this says in the definition, we never consider what happens when x actually equals a. And we're going to use and partially abuse that property here. So this is the derivative for the function f of x equals x squared. All the work here is legitimate and correct. In the green box is the limit definition. We'll see this quite often in Calc 1. The first step is simply plugging what f of x is, expanding out the x plus h binomial, canceling out the x squared, factoring out the h, going here and here. So the two things I want to point out to you are why this step is true and why this step is true. Now, this step is true because I've canceled the h's out. And the question is, why can I cancel the h's out? Because here we assume that h does not equal 0. But then the weird thing is, in the next step, we set h equal to 0. And in a very weird thing that I kind of call the voodoo here is that what the limit allows you to do is to assume that h isn't 0, and then immediately afterwards set h equal to 0. So you can kind of get away with both things because of the structure. And again, the basic idea of a limit is what the function should be. So if I look at this expression here for h very near but not equal to 0, it should be the value of simply 2x. Okay? Any other questions? Feel free to let me know. Thank you.